Hello and welcome back to Calculus 3, section 15.4 on the chain rule. Now, chain rule as a concept, we are going to learn the way to develop the formula for chain rule because each situation we see will be unique. The formula changes depending on how many layers of functions you have, how many independent variables you have or parameters. So all of those things are important. Let me give you an example. You can have, let's say, variables x. Why is this red now? Oh, thank you very much. Because over here, whatever. No, got it, thank you. What was I saying about variables? You have variables x and y, and those two apply to some function f going to give some output. And then you can have x and y using a different function g give some output, and then these two together in a function age, and it gives some output. Right? That's a possibility. And then you're going to have one configuration for a chain rule. Or you can have, let's say, x, y, z go in a function f, and then has an output, and then maybe just x and z go into different function g, gives an output, and then that in another function gives an output. So there are many combinations that you can have, and you can see this is the same input, right? xy in a different function, and then the outputs of that will be again driving some other function. Over here you have 3 inputs, and then only 2 out of 3 for the other one. So you can literally have anything. We are going to start with the simplest case, and please remember that your job here is to learn to make the formula. Then you can just plug stuff in. That's not a problem. And the way you're going to work this formula out, if it helps you, is to draw a tree of, and the book does also the same tree approach. So let's say that you have z as a function of x and a y, and then you have x as a function of t and y as a function of t. So this is the cheapest possible configuration for a chain rule that you can see. So what are we doing here? We start because we are looking for the derivative of z in respect to t. That's what we're looking for. You see that your t drives x and a y, and then x and y drive z. So you have layers, right? You see that you have layers. So to draw the tree for this, we say variable z is obtained by x and a y, and each x and a y is driven by t. I'm going to make this tree one more time looking at my functions. Here we go. So variable z is made of x and y, and then both x and y are each controlled or made of t's, whatever. So now if I want to find the derivative, and I'll write this in blood, split, use partial, straight, use these. So what is the derivative of, actually you have to use, you don't have to use, but you can use regular one because there's only one z and one t. So what is the derivative dz dt? Well, you have two branches. There is, let's go with the orange branch and the blue branch. So going down the orange branch to reach to t. So you are looking for derivative of z in respect to t, so you have to go in a tree from z to t. Every branch that has z to t, you have to go through it. So z splits into x and a y, so partial z partial x, and then you have dx dt. So we are using regular derivatives because, well, you'll see when we do the example why. And then you have plus, and then we have another branch, which is the blue branch, partial z partial y. Remember, it was a split there, so you have to use partials. And then you have dy dt. So this is our first order of business, to figure out this formula, looking at the tree which was obtained from functions that you have. And then you get to plug in whatever values you have and compute this. So let z be x squared y minus 3x. Let x be t squared, and let y be, I don't know, 1 over t, whatever. So this would be the example for the configuration that we have above. So now you see why you can use the regular derivative for dx dt. It's just a regular calculus 1 looking problem, right? Where for this one, when you are taking derivatives of z, well, you have partials. You have in respect to x and in respect to y. So if I want to find the derivative dz dt, partial z of x, that's going to be what? 2x y minus 3. Well, maybe I should use orange. So 2xy minus 3. So that's my partial z partial x, and now dx dt is 2t. And then I have plus. And now for blue, dz dy, well, that's just x squared times 1 over t squared, negative. Now, are we done? Well, we are not done, because we have x and y and t, so we have to bring all of these into t's, because your answer needs to be in respect to t. So you are not allowed to have any x's or y's floating about, so you have to use these equations to eliminate all of your x's and y's and turn them into t's, and then do more algebra to simplify all of this. So let's go. dz dt is equal to 2 times x is t squared, y is 1 over t minus 3 times 2t plus x squared is t squared, everything squared, times negative 1 over t squared. So simplify it. One of the t's cancels. Well, actually, when you multiply with 2t, the t would cancel right there. So it's 4t squared minus 6t plus No, minus. This is one of the t squares will cancel, so t squared. So dz dt is 4t squared minus this is 3t squared minus 6t, and that's equal to 3t when you factor t minus 2. There we go. Yay. For the chain rule, you first need to be able to make the formula, and then you get to plug all of the derivatives. So I'll go again through the whole process here to make sure you understand what's going on. Yes?
In the beginning, you actually have it right there. You were finding the partial of z with respect to t, and then in the end,
yeah, there's going to be these. Yeah.
Is that the same thing? Or?
You can actually use partial all the time.
Okay.
100% of these, but I like to use both of them because when you have your function depend on only one variable, that's a regular derivative. When the function value output depends on multiple variables, you would use the partial derivative. So some of these, right, if they're all constantly branching, you would have all partials everywhere. And if you have all of them be driven by only one variable, then they are regular. So this is why I said split use partials and straight use.
So it's really a partial until we substitute in all the x's and y's. Okay.
So why is this the cheapest case? Well, z is a function with two-dimensional input, and you have x and a y to be driven by a single parameter t. Yes?
If you know the values of x and y, why don't you just plug it together?
You can, but sometimes it's annoying. Remember that you have in Calculus 1, when we teach, I'm not sure which way you were taught, but when I teach chain rule, I ask students, what is the derivative of x plus 2 squared? And everyone goes, oh, that's easy, you just make it into x squared plus 4x plus 4, and then when you differentiate, you get 2x plus 4, and you're done. And I said, well, that's great. So let's just change this to 209. And then they said, well, now it's not really efficient to FOIL this, right? So let's learn the chain rule, right? So now it's 209 x plus 2 to 208 times the derivative of the inside, right? So you will not always be in a position to make it, right? So it's, nice. And you want to know the chain rule. I mean, obviously computers do all of these things. You don't want to know any of the stuff that you learn in school, but for the purposes of the exam and the next course, right, you want to know the chain rule. You will use it in DFQ at least once. Yes?
So if there's another variable, like it was, say, w, x, y, and z.
Oh, hold on, comrade. That's the next step. Yeah, right? We are going to get there. We're going to be three variables driven by three parameters. It's going to be epic, but hold on. Let's get there, right? One step at a time. So the next upgrade would be to use, let's say, three variables to drive and then have one parameter each. So say w is equal to f of x, y, and z. This is a fourth-dimensional function. Let's say that w is the temperature, okay? And x, y, z would be location inside the object. So currently my head is very comfortable with the temperature around it, right? And my head is in a particular x, y, z location. Now, if I am to move somewhere else, my head would be in a different x, y, z location, and that particular location might not have a temperature that I like. Let's say I sit directly under the air conditioning unit and it's just constantly blowing the cold air into my head, right? So in that case, that particular x, y, z location would have a lower value for the temperature in that region than the temperature where I'm sitting right now. So you can understand the fourth dimensional function in that sense. XYZ is a location in space, and that at that location, the variable W can measure the temperature, can measure the pressure, can measure the amount of light in lumens, right? You can do a whole bunch of things that you can measure with W once you provide the location where it is. Now, each one of these, x, y, and z, is going to be a function of one parameter t. So let's go g of t, age of t, and let's say k of t. So now, what is the tree diagram? Well, your variable w is measured by x, y, and z, and then each one of these is controlled by a function of t. So now if I want to find the derivative of w in respect to t, again, I'm using the regular d because there is only one parameter t as the independent variable. So I am going to use dw dt. Now what do I have? I need to have branches that go into from w to t. So I have my orange branch here that goes from w to t. I have my blue branch, and finally I have the purple branch. So for the orange branch, again, we have a split here. So on a split it's partial w, partial x. Now we're going down the orange, and then the x dt as a chain rule. Plus, blue line is going to be partial w, partial y. Partial w, partial y, because you have a split from w into y, because they're also x and z. And now when you get to y, it's a straight through derivative dy dt. And finally, the purple, partial w, partial z. So that's going down the last branch. And then finally, dz dt. If you are issued functions, you will plug the derivatives into the formula, then replace every x, y, and z with the other functions of t, and eventually simplify everything into single. Yes?
Will we ever be given something where an input, like say z, be given two inputs, so we need to do another, like a second partial onto there?
That's going to be for multiple, yes.
Okay.
So, again, we're getting there.
Okay. Yeah.
But that's a good question, because, again, I said, right, in the beginning, any combination you can think of, you can plow through. You just have to be careful. Splits, going to be partials. Straight throughs are going to be regular derivatives. Let's take a look at an example where function z is given as a function of x and y, and now x is given as a function of t and s, and y is given as a function of t and s. So now I have two independent parameters that will be driving x and y, and then x and y would be driving a z. Well, now you have two independent ones, so you will have to calculate, and this is your question, you will have to calculate two separate partial derivatives. So there will be a dz dt and dz ds. Now these are all partial ones, because you will see that it splits when you make a tree, it splits. So z is controlled by x and y, and then x is controlled by t and s, and y is controlled by t and s. So please note that this branched twice, And now we are going to have an orange path connecting z to t and then connecting z to t. That's the orange path. And then you will have a blue path connecting z to s and another z to s. So your partial derivative of z in respect to t are the orange paths. So you will use partial z, partial x, and now you have to use partial x, partial t, because x splits as well. In a previous case, x did not split into two. X only had one. So we use the regular derivative. Now it splits. Plus the second branch, partial z, partial y, and then partial y, partial t. So note that dimensionally, if you are to cancel dx's and dy's, you have dz dt, dz dt. You have to be able to do that in every formula you develop. It will always have that feature that if you cancel this intermediate derivatives, the one that stays is exactly the same as the one, because you can only add apples into apples. You can't add 3 apples plus 2 apples and get 5 frogs, right? It's apples plus apples, you get apples.
What if you use the apples to bring frogs?
How?
Eat them?
You don't eat apples. They don't know. Apples are bigger than frogs. Yes?
How bad will this get on the day? 4, 5?
Since you have a question, sure. Exam question, you will actually have 2 questions. One question will be very elaborate tree and you stop, and the other one will have functions where it has one of these cheaper cases, and then you will actually have functions that you compute to come up with the answer that is, in terms of t, like the previous example we did. So there will be two questions from chain rule. One will be just the tree, the other, because it will be elaborate. Let's say you have 3 variables and 3 parameters, so it branches into, right? And then the other question would be something similar to what we had earlier. So you have something that it's quick, right? So it will take half a page, right? I shouldn't say quickly write down, but I'll just say write down. Now the blue ones are the ZDSs, because you don't get the derivative that has everything in it. There is no overall derivative for this problem, because you have how many derivatives you get to have? It's always the same amount as the amount of independent parameter variables you have. So if you only have t, then it's only 1. So you should have only 1 derivative for the whole problem. But if you have s and t, you will have 2 formulas, one for s and one for t. If you have RST, you'll have 3, right? I.e. the exam questions, I said it's going to branch and branch and branch and branch, right? Well, we'll do one of those now. So following the branches, the blue branches, you start at z and you see a split, so partial z, partial x. And then you are at x, it splits again, so partial x, partial s. So when we follow the blue path on the left side, from z to s, you have to go through x, and you see that if you actually cancel x, you get the z ds, so we're good. Plus the other blue path, which is the other branch, is partial z, partial y. We're going to the y branch now. And then y branches into t and s, so partial y, partial s. And in this case, you have 2 formulas because you had 2 parameters. Now let's take a look at some of these that branch even more. So let's say that w is the function of x, y, z. I'm going to regret this. And then x is a function of r, s, and t. y is the function of s and t, let's say, and z is the function of r and s, whatever. So this is, let's say, a typical exam question where you have to draw the tree and write the formula for chain rule. So what do we have? Well, you first draw the tree. W splits three ways, x, y, and z. Now your x splits three ways into r, s, and t. Your y splits two ways in s and t. And your z splits two ways into r and s. As I said, you can have any combination imaginable, right? One of these could have been just one variable. You know, let's say y could have only be dependent on s, let's say. So you can have any amount of variables in f. That's going to tell you how many branches you have from w. And then when you get those, then each individual one will tell you how many branches that one brings. So now, what are all final destinations? Well, you have a final destination in R, and then one in S, and one in T. So you can write three different derivatives, chain rule derivatives for this, because, partial ones, right? Because you have three independent parameters at the end, R, S, and T. So each one of those will have its own formula. So when you start, so here we go. I'm going to use orange, and orange is going to go into R's. So W through X into R, that's one branch. There is no R under Y, but then there is R under Z. So my derivative, partial W, partial R, is going to have just these two branches, so two terms. First one is partial W, partial X, and then partial X, partial R. If I cancel X's, I see dW, dr, I'm good. Plus, the second branch that goes from W to R is partial W, partial Z, partial Z, partial R. If I cancel Z's, dWr, good. And we are done. There are no other paths that you can take from W into R. Now we go the blue path, W into S. So I can go through X, I can go through Y into S, and I can go through Z into S. So partial W, partial S, partial W, partial S will have three terms because there are three blue branches that went from W into S. Let's go. Partial W, partial X, partial X, partial S. Plus partial W, partial Y, partial S. Plus partial W, partial Z, partial S. Three blue branches because three of these ended up with S, and we have three terms to get our chain. And finally, we have red paths that go into T's. One through X and one through Y. So partial W, partial T is partial W, partial X, partial T, plus partial W, partial Y, partial T. I can't show both. You need to see the tree, and then you need to see the formula. Is there a formula that you memorize for chain rule? No. Every problem has its own formula. You need to learn to make those formulas. Tree is used to give you a visual approach to come up with those formulas. Then, when you have the formulas, you look at the problem, what the functions are, and then you plug in those derivatives. Anytime you have a split, it's going to be partial derivative. Anytime it's just one variable driving it, it's your regular derivative. So you can nest, and does it have to end with this? No, you can have layers upon layers upon layers, right? All of these are like two-step, right? You go from W into X's and then from X's into these parameters. So that's 2 steps, right? But you can keep adding extra layers because you can have nested functions, right? You can have, remember that you, in Calculus 1, you had the function that was, let's say, sine squared x, and there were 2 functions, right? The x squared was the outer function and sine x was the inner function, so there was just the plain chain rule that you had for sine x. But then you had the one on steroids, right, which was sine squared x cubed, right? Now this one has multiple layers. You have x squared on top, then sine x buried within, and then you have x cubed on the third layer. So you have 3 layers of functions in that case. You can also easily make 4 layers and so on. So if you don't understand this, I just taught that lecture yesterday. So on the YouTube stream, when you're looking at this one, just scroll 3 lessons up or 4 lessons up. You're going to have the entire Calc 1 chain rule lesson. So now when we go into Calc 3, all of the problems I did today, all of them, were of this kind. Because you had step 1 to go from f into x, and then step 2 from x to t, right? So all of the problems were just 2 steps. Yeah, sure, this one branched out a lot and had a lot of, right? But they were all 2 layered. I can add more. I can tell you that every r is driven by a and b, and then s is driven by, right, a and b, and then t is driven just by b. I can do that. Then these become your variables, the main variables, right? So it doesn't matter how many levels you have, it's always the same pattern, and it propagates through whatever number of nested functions you might run into. And the nested functions are something that you guys have in nature, right? If you take, well, my bag is not good, but this bag is awesome. I borrow this thing, right? So we call this a book or a book bag because he's sitting in a classroom and probably there will be books and computers and stuff, right? So function of the bag is to hold stuff. Now, and that will be your f of x, right? And then what goes inside the bag is a g of x that has a function, determines actually what happens with the whole system. Because if you are to go to the gym, you don't bring books, right? You put your gym gear. You put a parachute in this if you want to jump out of an airplane, right? Well, maybe you want to put the bag, but that's okay, right? Still, it's a bag, right? It's a bag. You go camping, you put the camping stuff in, right? If you're a hitman. Yeah. So the bag is the bag, right? And that's your f of x. And its function is to hold stuff. Then you put some other stuff. What is the g of x for a book? Well, you read it, right? You learn stuff, or notebook, you write in it. So all of that stuff that you put in here has its own function, and you plug that one into this one, and then you carry everything together, right? So you can, now, what do you have? You have a $10 bill that you can buy stuff with, so it has a function. You put that in the wallet that has a function to hold the money. and then you put the wallet in that bag, so there's your 3 layers, right? The money is in the wallet is in the bag, right? And then the bag has its own function. So 3 layers. Now the bag goes in a car has a function, right? And then you park in the garage has a function. So now $10 bill is under 5 layers of a function. The garage can be a part of a house, and the house is a part of the neighborhood is a part of the town, and the town, right? You see that? So you can, and each one of these concepts has its own function, and we can keep nesting like this. So in mathematics, you can keep nesting as far as you want, right? As far as the application needs you to nest. You don't just go forever. So all of the chain rule problems will have the same feature. Step number 1, develop the formulas. And you develop the formulas by creating the tree, which you got from what you have up there. Now, if you did not understand the way to make the tree, looking at the functions, I will point out one more time over here. Please look at the screen because you already have all of this written. The variable w is driven by x, y, z, which is why w branches into x, y, and z. You have to provide x, y, and z in order to calculate w. So that's why w branches into x, y, and z. Once we have that branching done, then you go and you take a look at each individual x, y, and z and see what they are driven by. And you see that x is driven by 3 variables, RST, which is why x branched out in RST variables. Then you have that the second part over here, that the y branches only in S and T, no R. Fine. So y only branches into S and T. And then finally, on the last row, R and S for Z, and here it is R and S branch for Z. So whatever functions are given to you over here, they will govern the way your tree looks. Then you go here and you say, well, we have a lot of independent variables, in this case 3. That means that we will have 3 chain rule formulas, because the number of these variables, and in this case is 3, R, S, and T. I don't care that they're not all present all the time. The most that you have are R, S, and T. So you will have to have 3 separate chain rule formulas. One that starts with W and ends with S in R, one that starts with W and ends in S, and one that starts with W and ends in R. Or T, whatever I didn't say. I lost track. I lost track of this about an hour ago. Does this make any sense? All right, thank you.
So in the end, for say that example, what does like partial W, partial R stand for? Is it dependent on the situation?
Well, that's your application, right? Because remember, your derivatives are your rates.
Okay.
So you are measuring the rate because, okay, so, right? That one did not go along x-axis, y-axis, z-axis. It went under combination of them. And it was a parabolic motion, and it had the velocity. So now, if I want to find which way it went, I have to decompose x, y, z. So now I have, and it all happened in time. So I have partial x in t, partial y in t, and then partial z in t, right? Because it went on that odd angle. If I threw it down the board, then it's a Calc 1 problem, right? Because it only went along one dimension, and because it went down the one dimension, you just use that dimension and time. So if it goes down the z-axis, like we said, this is going to be z for us, right? Then it's just dy dt, which is the velocity, right? So these are the things that, this is what's happening and why it's happening. Okay. Anything else? Well, let's do another example from. Let's do another homework example. So this way. Pick something. Let's see. Okay. You are going to see stuff like this on your homework, most likely. So this is what it says. ZS and ZT where z is equal to e to the x plus y, x is st, and y is s plus t. This is all you get. That's it. Let's start branching. What do I write first? Z. Z is on top. Now, what's the next layer?
X and Y.
X and Y. We see that Z is governed by X and Y. So Z branches into X and Y. Now, what happens with X? Has S and T. And what happens with Y? Has S and T. So we don't care what kind of functions you have. It's just what's the number of variables as you go from layer to layer. That's all we care about. When you are at the bottom layer, you say, I have the world of S and I have the world of T, and this is why they're asking separate ones, right? Because you can only make orange branch go from Z to S and a blue branch go from Z to T. So my orange branch, partial Z, partial S, which is your ZS. That's ZS. Partial Z, partial X, partial X, partial S. So that's going down the first orange branch, plus partial Z, partial Y, partial S. That's going down the second branch we have. And then for the blue one, partial Z, partial T, partial Z, partial X, partial T, plus partial Z, partial Y, partial T. Nice. We have the functions. It's time to plug in. So what's ZS? Partial derivative of Z in respect to S. Well, we have partial Z, partial X. What's partial Z, partial X? E to the X plus Y. Same thing. And then times what's partial X, partial S? Very good. Plus. Yeah, I mean, I gave you enough time. You know that if I'm taking partial in respect to S, S is a variable, T is a parameter. Or it's like having like 2S or something. So it's just T. And then we have the partial Z, partial Y. It's still going to be E to the X plus Y. And what's the partial Y in respect to S? It's 1. Because it's plus T, that's why. The derivative of T is going to be 0. No, it's way too late tonight. It's late. Right? So that's it. And now you have to plug in the functions and make this pretty, right?
How do you get rid of that t?
No, you need it to be.
Don't you need it to be in terms of s?
All
That's one a little confusing.
I don't know.
That's helpful.
It's a derivative in respect to s, but yeah, well, let's see. It's going to get somewhere eventually. So partial derivative in respect to s, we have e, and then I have t plus 1, right, as if I factor out. X is given as what? St plus, and y is given as s plus t. There you go. The derivative is respect to s, but t is necessary evil that it's there.
So you just leave t in there. Okay.
Yeah, because you know what the s and t are at all times, because those are the things that you're measuring.
Okay.
So that the derivative, when you're doing the derivative, you are going into those variables, but you are not allowed to have any of the x, y, and z's in any of these. So what do I have here? I have s plus st plus t, whatever. There you go. Done deal. And now the blue one, that's a zt. So what's the partial in respect to t? It's going to be e x plus y s plus e x plus y times 1. I didn't even see the functions that I know already. How do I know this? Well, these functions are symmetric. Now, what does it mean? Symmetric function. If you have two variables in a function and you swap them, the function actually didn't change. If I change x with y, because they're added, the function doesn't change, right? Because it's still x plus y, now y plus x, no difference. If I change st into ts, no difference. If I change s plus t into t plus s, no difference. So if you have subtraction and division around, then yeah, they're not symmetric. But if you have only addition and multiplication, they tend to be symmetric, and that's why we can do stuff like this. So now the answer is exactly the same, where all s's are t's, or all t's are s's. So zt is s plus 1 e to the t plus ts plus s, because it's symmetric. Or if you do the calculation little by little, you'll get the same answer. So you'll have a lot of this kind of chasing around to get to good? More examples? Or this was enough? Pretty good? Why is this curvature here? All right. Well, that's the chain rule then. Bye.